So in the last video, we were talking about the phase angle, and as an illustration of what that is, cosine of theta is equal to sine theta minus pi over 2. Think of an example. If theta itself is pi over 2, the cosine of pi over 2 is 0. The sine of pi over 2 minus pi over 2 is sine of 0, which is 0. So the difference between the cosine and the sine is this phase angle, right? It's a shift. So this phase angle phi allows us to tailor make this equation into what we need to match our initial conditions, what a physicist would call the boundary conditions. So this is actually the general form that we're going to stick with. Very often phi is 0. Very often you actually do start it over here. So if that's the case, then this you can just throw it away and go back to this one. But this is the most general form. So this is what we're going to stick with. X of t is equal to a cosine omega t plus phi. All right. That is the first equation of motion we've seen. What I'm going to do now is I'm going to rewrite that in its simpler form, right? We're going to assume that phi is 0. Of course, it doesn't have to be, but we're going to assume it is for the sake of simplicity and just write our simplified form. X of t is equal to a cosine omega t. Okay, so we now know the position as a function of time. But we also know some things about the position function and its relationship to other functions. We know that velocity as a function of time is just equal to the time derivative dx of t dt, the time derivative of the position. So if I take a time derivative of this, I'm going to get, well, a is a constant, it's going to come out. And then I'm going to take a derivative of the cosine. But the cosine, I have to, by the chain rule, I have to take a derivative of the argument of the cosine. If I do that, omega is a constant, and it will come out of the integral. So outside my two multiplicative constants are a, just because it's constant, and then omega, the constant from applying the chain rule, omega. And then the derivative of the cosine is the negative sine, so I need to put a negative here, and sine omega t. So I have arrived, just with a little bit of simple calculus, at the velocity as a function of time, or at least the speed as a function of time, minus a omega sine omega t. I don't have to stop there, of course. Acceleration as a function of time is equal to the time derivative of the velocity, also equal to the second derivative of the position. I keep putting my parentheses in the wrong spot. That's okay. I'll write this in a second. Second derivative of the position, I'll write that in a second. Let me just take the derivative of the velocity here. I'm going to get a minus a omega from the constant. And then I'm going to take the derivative of the sine, and by the chain rule, the derivative of the argument. I'm going to get another omega out of the chain rule, so let me just put the omega squared there. And then I'm going to get cosine. Derivative of the sine is the cosine omega t. And there it is. Those are the three equations of motion for this oscillating system. I get the position as a function of time is a cosine omega t. Speed or velocity as a function of time is minus a omega sine omega t, and then the acceleration as a function of time minus a omega squared cosine omega t. All right, once I have that, I can do something really interesting. Let me just write down Newton's second law. So this is, you can think of it as it's not a kinematic approach. These aren't kinematics, but we saw this in the context of kinematics, right? But that's not the whole story. We've got to be able to analyze the forces. So the net force acting on here is just going to be the spring force. And of course, this is equal to MA, because the net force is MA. But I'm ignoring all friction and everything, so all I get here is the spring force minus Kx, where K is the spring constant. All right, well, let me rewrite this. MA is equal to minus Kx, just because I like what I'm solving for to be over here. This means, of course, that the acceleration is minus K over mx. Now, let me rewrite the acceleration as the second derivative of position. D squared x dt squared is equal to minus K over mx. This is actually a very important equation. This is called it's a wave equation, and the solution to it is that it's a second order differential equation. I should point that out. Fortunately, we already know the solutions to it. If you've been through a differential equations class, you know that finding the solution to differential equations is not always easy, but we actually know the solution to it. It's right here. So when I have this now, I can plug in d squared x dt squared, which is here, and I get minus a omega squared cosine omega t is equal to minus K over m, and instead of writing x, I'm going to write what x is, a cosine omega t. That's very interesting, right? I've got this cosine omega t in both terms. I've got an a in both terms, and I've got a negative sign in both terms. Okay, well, let's get rid of all that. Get rid of the negative signs, cancel out the a's, cancel out the cosine omega t, and what I'm left with is omega squared from here is equal to K over m, which means, of course, that omega is root K over m. Now, what is omega? Omega is the angular frequency. That's very interesting and also very, very useful. This tells you that the angular frequency of this motion is a function of your physical parameters. Now, this is a physical system. It's a physics class, for goodness sake. It hopefully at this point in the semester doesn't surprise you that the mathematical characteristics are going to be determined by the physical characteristics, but it's still cool to see. So the angular frequency of this motion, this mass on a spring, is given as the square root of the ratio K over m, where K is the spring constant, and m is the mass of the thing attached to the spring. So we have now basically completely characterized this system to the extent that we want to. There are a couple other things to look at, which we will do later, but this is a really good start on understanding cyclical or oscillatory motion, how to describe it mathematically, how to get information out of these equations. So hopefully this was clear and easy to follow. There will be more videos to come later.